academic and researcher in the Department of Physical Science at the Universidad Andrés Bello in Chile since 2016. She made her PhD thesis in astronomy in Cornell University in 2011, and she has been a postdoctoral researcher, first during 2 years in the American Museum of Natural History, and then in the Instituto de Astrofísica y Ciencias do Espaço in Porto, Portugal, for another 3 years. Since November this year, she will be associate professor at the Instituto de Alta Investigación de la Universidad de Tarapacá in Chile. She's got a remarkable observational experience and also in supervision of a number of students, pre- and postdoctoral students. Her areas of scientific interest are the red dwarfs, brown dwarfs, and exoplanets, where she has developed spectroscopic and photometric methods for the classification in the visible and in the infrared. She's got a quite important number of papers, including in Nature. She's leading a Chilean project since last year. She got the prize 100 leaders, young leaders, so 100 líderes jóvenes in 2017, and the Roger Doxey Prize winner from the American Astronomical Society in 2012. She's also interested in scientific dissemination and initiatives to promote diversity in STEM. Her latest works and advances related to the metallicities of M-dwarf stars is what she's talking today about, and the challenges that the cool dwarfs photospheres still present to us, and she will also discuss what else is needed to attain precise and consistent abundances and the implication, the impact in the models of such stars. So thank you very much, Barbara, for coming, and we will be listening to you in the next 14 minutes or so.
Okay, thank you everyone for coming. I'm really pleased to be here. I wanted to thank Pedro for organizing a workshop that several of the people that are here, we interacted, we talked about this, right? Metallicities of M-dwarfs. Probably some of you don't care about M-dwarfs, and basically this talk is for you. It's not really for the people at the workshop, but it's really for the people that may be wondering, so what? Why we care about the metallicities or any sort of parameter for M-dwarfs. So what I'm going to do is going to start describing what an M-dwarf is, and then I'm going to go kind of in a historical way, mentioning why we want to know the metallicities of M-dwarfs and what do we know, what do we mean by metallicity, and what are the challenges that we are having today, okay? So here we are. So what are M-dwarfs? M-dwarfs are cool, small, numerous, and faint main sequence stars. That means that when we look at the HR diagram, I don't know if you have ever seen an HR diagram like this one. Usually, if some of you have taught or have taken astronomy classes, usually they show you this plot till kind of here, from here up, right? Here, I'm showing you a bunch of objects that usually are neglected when we look at the HR diagram. So here, this is a color magnitude plot. So here we have the absolute magnitude in H. We have color, J minus K. We see where the dwarfs are. So are the stars here. And then we see where the M dwarfs reside. We see that actually these stars are extremely faint when we compare it to other stars, for example, like the sun, and that they cover a large range of magnitudes. Roughly, their parameters like effective temperature, mass, and radii basically are within these values. And specifically, this value is because that's the minimum mass that it's necessary to have fusion in an interior of a ball of hydrogen in hydrostatic equilibrium. Okay, so anything that is less massive than an 8% of the mass of the sun will not be a star, and it's something that we will call a brown dwarf. Brown dwarfs are exactly the things that you start having here. Okay, those are objects that some of us think that they are formed as stars, other ones think that actually they're formed as planets, and that's a big discussion, and that it's another talk. But I want you to basically see what we are able to do now with the new telescopes, with the bigger telescopes, and actually also with near-infrared data. Right? We are able to see things that when we only care about B and V, we were unable to see. The description of what are M dwarfs comes from already 1943, and it's basically stars that show titanium oxide / molecular absorption. So what I show you here in the first plot, it's optical spectra of different stars. They are all dwarfs, but they have different spectral types. So we have an O5, an A1, a G2, so this will be basically our sun. Then we have a K0, and then you see what will be the expected spectrum of an M5 star. And you see that it's very different from anything that they have told us when we were young and said that stars were black bodies, right? It seems that something was wrong with the spectrum, the spectrograph, because I have a lot of flags that seems to be missing. And that's basically the main characteristic of these stars. This missing flags is basically molecular absorption, it's opacities, okay? And in the other plot, I show you kind of the reddish part of the optical spectra where you can see in low resolution the titanium oxide bands, the calcium hydride bands, the vanadium oxide, and also atomic lines that are present embedded in this forest of lines. So this is low resolution. Imagine the nightmare of a high resolution spectra. You would see this basically, okay? And that basically tell us that these are complex atmospheres, right? If we want to model them, it's a really big challenge. M dwarfs, as I said before, are what we should call the smallest stars. Anything that is less massive than 8% of the mass of the sun, it's not a star. And I just want to show you how the spectra actually changes when you go toward smaller masses and therefore to lower temperatures, okay? So while I tell you that M dwarfs atmospheres or photospheres are complex when we maybe compare them to stars like our sun, clearly there are way much more complex atmospheres as well when we go towards the lower temperatures and we go to the brown dwarf and even planetary regime. So why do we want to know metallicities of M dwarfs? When we talk about metallicities, what we really are talking is we want to know the abundance of one of the heaviest thing, and it will be the abundance of iron basically in these stars. And one of the things that it was first thought that M dwarfs can contribute and the metallicities of M dwarfs can contribute was for the studies of our galaxy. Why? Because they're a big component, a stellar component of our galaxy. Here I show you, let me see if I can come back. There you go. Here I show you some images so you can see that actually M dwarfs, for example, sometimes are companion, common proper motion pairs with other sorts of stars. Sometimes you can have two M dwarfs together. There you have, you can have maybe an M dwarf and a Y dwarf. And what means is that actually M dwarfs are the most numerous type of a star. Like if we think about it, it's about 70 to 74% of the stars of the galaxy are M dwarfs, okay? Here I show you a little movie done by Riddle, Adric, where it shows you all the objects that are within 25 parsecs from us from the Recon survey. The RECON survey was a survey that has been for a long time obtaining parallaxes for these stars that were ignored by Hipparcos. Now that we have Gaia, that it's not going to happen. But they have worked for several years trying to know the distances for these objects that are too faint for Hipparcos. Okay, so everything that is reddish and kind of orange are M dwarfs. If we go to 10 parsecs, this is what we see. So we have no O stars, we have no B stars. We have about 20 stars that have a G type, but there are about 246 stars that are M dwarfs. Okay, our closest star to the sun, it's Proxima Centauri, and it's an M dwarf. It's a star that it's not in any of the constellations or any of that because it's too faint for our eyes to see it. And it's the closest star to us. Okay, so in 10 parsecs, there are 12 times more M dwarfs than G dwarfs. Why they're important as well for studies of the galaxy? It's basically because they live forever, right? The current age of our universe, we can put it between 13 to 14 gigayears, right? And maybe 15, depending on which is your source of papers. But these stars have lifetimes that are trillions of years, so 10 to the 12. None of these stars, even the first ones that they were formed, have evolved. They haven't become the helium white dwarf that we expect them to become. So what you see here is basically theoretical evolutions of what we think will happen to M dwarfs. So each of these paths show you different types of masses. And in this little plot right here, shows you the mass versus the lifetime in trillions of years. Okay, so it will be 10 to the 12 years. And you can see that as you go to smaller and smaller masses, the lifetime, even in trillion years, gets larger. So these stars basically remain the same for trillions of years. It's not like other stars that they evolve and they become giants, for example, and then their photosphere changes. Even when we try to say, no, it's the same metallicity, really M dwarfs should be the perfect targets to do studies of the chemical evolution, for example, of our galaxy, or even the dynamical evolution if we were able to see them. The problem is that they are too faint. They dominate in number. They are the ones that basically remain doing the same for many times, but they're just too faint for us to basically use them as traces for these things. This is one of the applications, for example, to study ame objects that come from different parts of our galaxy. This is a reduced proper motion plot, which is similar, for example, to a color magnitude plot, but instead of using distance to get the absolute magnitude, you can use the proper motion of the object, okay? And when you do that, you can actually see that the stars in our galaxy divide in two groups. So we have stars that are in the disk and stars that are in the halo, right? We think that stars in the halo are older, they should be more metal poor. And this is something that we see in the spectrum of these stars. And there is what we call a metallicity classification for these stars, which is based on what we call the zeta index, which is the value that you have here. But even when we call it a metallicity classification, what we're really doing is to classify these stars as members of different populations within our galaxy, okay? We have now tested that this is not really metallicity, but how do I say this? It links to metallicity. If a star is an extreme subdwarf, indeed it's metal poor, but there is no one-to-one correlation between the metallicity of that star and that zeta index. And you can see that as the stars become from dwarfs to ultra subdwarfs, for example, a star that exhibits really large, they have the kinematics, of stars in the halo, you can see that features do change, right? And some of them disappear. For example, here we have the titanium oxide. It's a molecule that is made of two metals, basically disappears when you go to an object that seems to be part of our halo, right? That should be a metal poor star, and that molecule basically doesn't form because there is not enough titanium and oxide to basically get together and create an opacity that will show us absorption there. Another reason on why we want to know metallicities of M dwarfs, it's a more recent one, right? We care about metallicities for M dwarfs since the 1970s. Now, since the 19s or maybe the 2000s, we care about metallicities of M dwarfs because we want to understand planet formation. Why? Because now we have surveys that are trying to find planets, and they have found quite interesting planets around M dwarfs. The most likely planets like the Earth are found around M dwarfs, not around G dwarfs. There is an explanation for that. It's basically the biases that we have with our searches as well, okay? But we want to know something like the metallicity for M dwarfs to also guess which M dwarfs should we observe if we want a certain type of planet. Why is that? Because since the discovery of the first planets in 1995, there has been an empirical relation that shows that the stars that had giant planets were metal rich. This is known as the planet-metallicity correlation, and these are kind of new plots from Adibekian 2019 that show basically that. So when we plot metallicity and we plot the number of stars that have planets against the ones that they don't have planets, we see that the stars that have giant planets tend to be more metal rich than the stars that don't have any planet yet detected. We have to remember that very well. It's not that the stars don't have planets, it's that we haven't been able to detect them till a certain distance or till a certain mass, for example. And here, for example, shows you basically the fits that several people there have done to this planet metallicity correlation for giant stars. And also you can see another plot here that shows single stars and stars hosting only low mass planets, and we see that basically those distributions don't change much. So it seems that metallicity really helps the creation of large, big, gaseous planets, but not necessarily the smallest planets that maybe some of us are more interested because they will be more like a second Earth, okay? This is also basically the same result. This is studying basically hot Jupiters, where they see that when they plot metallicity and the mass of the planet, you can see a relationship. This is also seen for FGK stars, but as we observe more and more M dwarfs in transiting surveys and RV surveys, we realize that actually M dwarfs don't seem to create a lot of these gas giants, and what they really have are Neptunes, sub-Neptunes, super-Earths, and rocky planets. However, metallicity is something that we should care still, because right now the most accepted method to create planets is the core accretion scenario. And metallicity helps exactly in this part, in the symbol of grains, little rocks, that then they will become a larger rock, and then gravity can take over to create basically the cores. Then they can, this cores, if they get massive enough, they can grab gas, then they will heat, the star will ignite, and for the less massive ones, probably that envelope will get missed. For the most massive ones, they will be able to retain that gas. And you can create what we will think of mini Neptunes, for example, and super Earths. This, what I'm saying is not that there are not giants around M-dwarfs, it's just that M-dwarfs don't seem to have giants. We have M-dwarfs that actually have giant planets. And now, because of this relationship, we may, and because it seems that also the most important thing maybe in planet formation may be the disk mass, M-dwarfs may be creating these giants in another way. And this is something that also was discussed in the early 2000s, that was another way to create planets, that it's the disk instability. That method doesn't depend on metallicity, for example. Now, things that we care about. What we were doing in the workshop for these past 3 days, we were trying to talk and discuss and show the work that we have done from having spectra and trying to get these values, okay? Mostly we were interested in this value, but basically when we look at spectra, what we really want to get is the effective temperature, the metallicity, and the log G. And you see that I put, kind of 2 arrows there and a person that is holding something, and it's a mess, right? And that comes from M-dwarfs being very cool. They have complex atmospheres because they have molecular absorption. And it's been a problem that was avoided for a long time. People didn't want to get metallicities of M-dwarfs because why? However, now we have a motivation, and I think the biggest motivation for it is that we're finding planets around these stars, and what we want are these values. These values are not hard, they're not easy to get for stars that are single. Actually, if we want to get a measurement of the mass independent one, we need to have a binary system. If not, we cannot get that mass. We can also get the radius if actually that is a binary system that it's eclipsing. We could get mass and radius for asteroseismology, but for M-dwarfs, that doesn't seem to be right now very possible for many of them. But there are works on that. Radius, we can get it for interferometry. However, our interferometers don't seem to grab a bunch of M-dwarfs because these ones are too faint, okay? So we have to rely on these quantities and use our favorite method, either using other luminosities or using evolutionary models to go from here to here, and from this mass and this radius of the star, go and get the properties of the exoplanets that we are finding around M-dwarfs. So yeah, the discovery of planets around M-dwarfs motivated a lot of people to go and get these metallicities because first, for example, we wanted to see if there was a planet metallicity correlation for M-dwarfs. The planet metallicity correlation that we saw was for solar type stars, and nobody had seen this for the M-dwarfs. So we need of alternative and exotic methods because they're complex. Also, they're faint. Trying to get a really nice high signal to noise spectra in the past in the optical for these stars was very costly, okay, in terms of observation time. And it was also a complex problem. So yeah, you can spend that time in the telescope getting the best spectrum that you can get, no tellurics and everything, and then you have to deal actually with all of this molecular absorption and all the degeneracies that this causes. So for a long time, since the 2000s, we have been developing methods to get metallicities from common proper motion pairs. Why? Because we assume that these common proper motion or binary systems were created from the same cloud of gas, and therefore, if an M dwarf is a companion of a star like the Sun or maybe a K dwarf, I know how to get metallicities of those ones, and I can assign the metallicities of the hotter object to the M dwarf. Okay, so that was a way to solve this. So there were, for example, color magnitude relationships based on absolute K magnitude versus V minus K short color. And here we see two. We have the one of Bonfils et al. In 2005 that he did for his dissertation. He was actually doing a search of planets with harps, and he wanted to characterize his sample, so he came out with this calibration that is photometric. We can see that all of these lines that you have here are metallicity, isometallicity contours, and they're based on common proper motion pairs. So I assign the metallicity of the hotter object to the M dwarf, and then I try to find a relationship between these two quantities, and then I can plot the other stars that I don't have any metallicity measurements and have a value. The same thing done here later in 2010 by 2009, Johnson and Apps, also because they had a survey. It was the California Planet Search Survey. They were looking at M dwarfs, and they wanted to know the metallicities of those ones. HARPS, it's in the southern hemisphere. The California Planet Search is in the northern hemisphere, okay? So they use different things. Something that I came out with is using not the optical spectra. At that time, I was doing my dissertation at Cornell, and there was a spectrograph being built. It was called triple spect. It's a cross-dispersal spectrograph that was covering simultaneously J, H, and K band at a resolution of 2000. And we said, okay, we have this problem of not knowing metallicities of M dwarfs. Also, some of the measurements were giving values that were not that reliable. What is happening with the M dwarfs? Do they need metals to create planets, or they don't need metals to create planets? So why don't we come out with something? And I use proxies, okay? When we think about metallicity, we think about iron lines. I didn't use any iron line. I used common proper motion pairs, and then realized that the strength of the sodium lines and the calcium triplet that it is in K band, if I was able to also use the water bands, will give me an idea of the metallicity of the star. And this is something that we have here. So I have the calcium equivalent width. It's really an index divided by this index of water. And here I have sodium by the water. And you see these lines that are the isometallicity contours, and we see a sample of 133 stars that I gathered for that. We have other things that were done and improved. This method was also observed with other spectrograph, with the specs, and there are at least 2 theses also coming out trying to improve this method and use maybe H band as well, and J band, and sometimes even including optical with another spectrograph. And for example, here I show you what happens with the M dwarf metallicity derived by this method versus the primary star metallicity. If they are coeval, we should expect, right, that there is a straight line. In this case, because it's a fit, actually everything looks fine, right? If I go and plot stars that actually were not in the fit, maybe this will not look so nice. There were other approaches. We were lucky enough that actually we start getting high resolution near-infrared spectrographs, and we could study these stars that indeed they are intrinsically faint, especially in the visible, but they're not so faint at the near-infrared. So we can spend less time observing them in the near-infrared and have higher signal-to-noise. Some of them were done in the optical, in the far red. Other ones were done in J band. Other ones were using different types of resolutions. When I talk about high resolution in the near infrared, it can be anything from 15,000 to whatever it is, right? Like higher. I'm not talking about maybe the HARPS resolution of 100 and something thousand, right? All of these were based on binary systems. We rely on these common proper motion pairs, and we said, okay, they should have the same metallicity, so we will find an index or something that gives me, you know, a straight fit, and then I can apply that to the sample that I want to know metallicities. Something also that David now showed us, this is one of his slides, I asked him to give this. It's also do this using this binary method of trying to get metallicities of M-dwarfs from the primaries. And the advantage of this one is first the number of stars that they have, but also that they're using the same spectrograph and the same technique to derive those metallicities. All the previous ones rely on derived parameters for FGK stars that were in different papers in the literature. So some of them come from synthesis, other ones come from equivalent widths, and people that have worked with FGK parameters, they know that they don't necessarily agree. So you bring a little bit of noise to that if you use different samples. In this case, they're using the same spectrograph. David showed us the results that they are getting from the primary and then using, you know, photometric relationships. And I guess since this is paper 1, there has to be a paper 2 where they actually gonna go to the spectrum, the spectra of M-dwarfs, and try to find things that they can work on, and maybe first see if actually the binaries have the same metallicities. That I think it would be a quite interesting thing. And also derive basically metallicities for these stars. However, things have been better and better with theory. Like now we have better synthetic models and we have better atmospheres, right? We have better sources of data. So here, for example, I show you some of the, I think this is probably the first paper that I read about metallicities of M-dwarfs. It's from '76 from Mould, where he was actually having a series of papers, and the second paper is about synthetic models for M-dwarfs. And there was a whole discussion about how H2 opacity, it was something that was extremely needed for the models, because if not, the models didn't fit the M-dwarfs that they have at that time. Okay, we go now to 2019. I was going to say 18. I live in the past. So, and now we have all of these models that are way much more complex as well, but complex in a good way. They're able to reproduce things that we're seeing in the spectra of the spectrographs that we're using, and they can help us to estimate the parameters that we want for our stars. Here I show you one of the slides that Andrea showed us during these 3 days. So this is a synthetic spectrum of a star that has 3,600 Kelvin, a log G of 5, and of solar metallicity, but with 2 different codes. And I think there is an intermediate one, but I think it's the black one, but we don't care about that one. The red and the blue are 2 models. They're current models, okay? They're from the past 5 years, yeah? And even then there are differences between them because they have included different sorts of equation of states, different opacities, in order to improve this method so we can use them to derive parameters for these stars. Something that I was really impressed on, this is my dissertation work. I I have never worked with near-infrared spectra. And at that time, it was a new instrument. It was something built home, right? It was built at Cornell. We didn't have a pipeline done for somebody that have worked on this to reduce the data. So we had to figure out ways to reduce the data, and we were never really sure with another grad student if the things looked good or bad. And I had to correct for the tellurics. And I always thought that all of this was residuals from the telluric division that I was the cleaning of the tellurics, until I overplot a synthetic model that was the state of the art at that time, the BD models, over the star, and realized that all of this was water absorption. And they were able to actually match every single one. So when I used to hear that, oh, synthetic models don't fit my stuff, yeah, it's true. They weren't fitting these lines, but come on. It's fitting all of the other part of the spectra, right? So the models are really, really good. It's just that they have some issues, and those ones have been, people that work in models, they know what they are, the restrictions, right? And they're trying to provide better and better things. This is something that happened, and Beta Pasager actually showed us. This is a recent paper. It's done with CARMENES data, so it's high resolution optical and near-infrared spectra. And she basically fit with the synthetic models, the SESAM models, the Phoenix SESAM models, lines that were not related to activity, or they were not affected by activity, in order to get parameters such as metallicity and temperature. They obtained log Gs from something, from another place, because it's a degenerate problem and they were having issues trying to fit the three things. And we can see that models actually are doing a pretty well job, okay? And we are able to derive, for example, metallicities using the VISANI and the near-infrared. And here is a plot with what we have in the literature and if they agree or they don't agree. This is important. Why? Because what we really want is to get closer and closer to what is being done for the FGK stars since decades. We want to study the M-dwarfs the same way, maybe not trying to find this alternative method so we can basically study them together. Something that I want to show you, and I didn't show anybody, so this is a new slide for all the ones in the workshop. It's the work of the student, my student with Elisa Delgado Menda. It's Pedro Sarmento. His PhD work was basically use the available spectra from the Apogee survey, that it's basically based on M giants, but within that sample there are a bunch of M dwarfs. And I said, look, this is a H-band spectra that is free, anybody can use it when they are released, and maybe it's something that we can test using synthesis, using the atmospheres that now we have. So this is a synthesis, for example, of an M-dwarf that has an apogee spectra. This is using iSpect, which is a code built by Sergio Blanco Quaresma et al. It used turbospectrum. Pedro selected a list of atomic and molecular data, and this is work in progress. He already submitted a paper about FGK stars. It's being reviewed and submit again, and this is what we can have, for example, for an M-dwarf. I was really impressed with this. When I was a grad student, I didn't think that this was possible. And now we can see that actually synthesis is doing a great job. What is the main problem that we have with this? It's the normalization. M-dwarfs have so much more molecular opacities that the normalization is not something that I just go and think that this is my continuum, this is my continuum. There are opacities, so what we can think is the continuum actually is data, okay? It's absorption. So that has been probably the most hardest thing to do, and we see a lot of degeneracies there, and Pedro has been fighting with that, but I think the agreement is quite nicely. For people that are kind of wondering what is this, everything that it's in gray are lines that are using the synthesis. The red one, it's basically a spectrum that it's constructed, right, from the synthesis according to the parameters that are measured from the lines that are the gray lines. Something that we also see today was the work of Tabernero et al. 2018, which is the method, the step-art syn. So this is also synthesis. And they have applied, they have other code that is the part that does equivalent widths. However, this synthesis one, they are applying it to Carmen's spectra, so they are applying it to M dwarfs, and this is something that they are obtaining, so basically are line by line. The green line, it says, is turbo spectrum, the red line is the Phoenix grid, and the black line is the observer spectrum. They're getting really good results. Things are fitting, and they are basically getting values for log Gs, for metallicities, and for temperatures without assuming one to be something. Okay, so breaking up the degeneracies, and you basically see here what is happening, right? Like that's basically one of the difficulties that we have trying to do this. There are other things. There are other people working on this. One of them has been Soto, also using apogee spectra. He has been focusing in specific stars that have planets, for example, from Kepler or other ones that have been discovered and are part of the apogee survey. And not only measuring iron over hydrogen, but also measuring other abundances. So here, for example, there are some lines, the CO, sodium, magnesium, aluminum, for example, that are giving abundances for those things. The top plot that you have there is from Bellet et al. 2017, that using near-spec data, they were able to derive basically titanium over iron. And here we have the Tsuji et al. 2016, where they're measuring basically the abundances of oxygen over carbon. So something that seemed impossible to me when I started working with them dwarfs when I was an undergrad, to try to study them as we study FGK stars, now it's something that we can do, okay? Here we have another approach, and this is using, all of this modern stuff. We just don't use more chi-square or anything like that, and we use the machines, and we want the machines to figure out alone by learning, machine learning, all of the things, and then basically give us the results. This is a work from Alexandros Antoniadis. Did I kill your last name? No. It was fine? Okay. Where I understand that this is not your thesis project, right? Your thesis project is for near-infrared spectra, though. Exactly. Okay. But he has been using HARPS spectra from M dwarfs, selecting the parameters of these objects, putting this there, and basically from this data set with a line list and reference parameters, he calculates pseudo-equivalent widths, and it has a data set of HARPS data. So basically this is where the machine got its learning. And then he can go and apply it to something else and get the stellar parameters. And he has been showing us really cool results, and I look forward to see what will be the results with all the suggestions that we gave you, because I think it will be something quite interesting, especially for any of you that is thinking of large data sets. I think this will work perfect for that. Maybe if you just want the parameters for one star, you can maybe do synthesis or something like this, but if you want, 1 million stars, this is something that can be very powerful. Now, the question you may be questioning is, how well do we know the metallicities? I think, and this is my own opinion, is that we have been able in the past years to actually give reliable metallicities for these stars within different methods. Most of the methods agree that something is solar metallicity. Within the errors, everything is solar metallicity. We don't have things that maybe are super solar and in other method are, extreme subdwarfs. So we at least can give you, even if the numbers are different, the thing seems to be agreeing. However, something that we really want is to have precision. Maybe for large surveys where we want to study, the galaxy, since we're studying such large numbers, maybe precision is not something that we need because we're looking everything in bulk. But when we're studying planets, it's something that we really want. And why is that? It's because we're discovering planets with what we call indirect methods, okay? We don't see the planet. What we do, basically, is see at the effect that the planet has on the star. So, for example, here is a paper, the paper of the discovery of the first exoplanet by Mayer and Kellos, that actually they got the Nobel recently. And we have the radial velocity curve, right? So you have the observations and then what they fitted. And the observable, oh, these things move. The observable is that K, and we see that that K depends on the mass of the planet and the mass of the star. So if we want to know the mass of the planet or the minimum mass, because there is also the inclination there, we need to know the mass of the star. Here is another example. This is, I think, one of the first transiting planets. And here what we actually measure is how dim actually the star gets as the planet basically is eclipsing the star, right? It's transiting the star. And that will be this, and we see that that value is proportional to the ratio between the radius. So if I want to know the radius of the planet, I need to know the radius of the star. So I think this is not that complex anymore, and we can do it. We can give values. We just not only say this is a metal poor star and this is a metal rich. We can give you a value. However, our precision is not that clear. And why we want this precision? Because people that work on exoplanets want to do this sort of plots. So here we have the planet mass and the planet radius. And here what we see are lines that are telling us which sort of composition those planets will have. So if I go and do a zoom of this part and I plot it here, and I plot some of the planets that are known, you see that we have large error bars. So even when this one is very close to a Mercury-like, just because of the uncertainty on the mass, it could also be an Earth-like planet. You could tell me, oh, but come on, they're all rocky, so what? Well, we care, because I don't know if it happens here in Spain, but in Chile all the time, every single week, there is a Earth point 2 being discovered. And I do a lot of outreach, and I have to go and tell people what that means, because people think that actually we found another Earth, and it's not really what we found, okay? So if we want to disentangle what is the composition and really what these things are made of, and then if later we want to go and see the atmospheres, and something that I learned actually at this workshop is that in order to estimate the abundances in the atmosphere of these planets, they use the metallicity that we derive for those stars. It's something that we need to care about. And why is that? Well, this image doesn't look very good. I remember that I had it and I couldn't find it, the high resolution one. But these are very well-known M dwarfs. Okay, they're bright, they have optical spectra since forever. We have observed it in almost every way. Actually, they have interferometric measurements. For example, Gliese 876, if you go to the literature can have a spectral type from M2 to M4. That's a big change in effective temperature, okay? Here we have Gliese 581. These two have exoplanets, and that's why also they have been studied a lot. Gliese 876 basically has two kind of big planets and one that it's a little bit smaller. Gliese 581 can have even 5 or maybe less planets, according to which word do you believe. And these are the values, for example, that I will have for effective temperature and for the radius, assuming that this is the luminosity and this is the distance for this star. And they compare what are the values that I get with different methods until that time. So using the near infrared, that will be my technique, K-band, fixing log G to 5, because I couldn't deal with that with my spectra. I have that these stars have, temperatures. Basically, I make the stars smaller and hotter than what the interferometric measurements are telling me. In the first case. In the second case, I can be like, they kind of agree very well, and we're happy, right? Usually we see this a lot in papers. My method agrees with interferometry when I just look one star. But when I go and look at the other one, it doesn't. Then when we go to methods that use optical low res, the star gets a little bit hotter, but also gets smaller in the first case, and the same thing happens here. I think, no, it gets larger and gets also lower temperature than the other one. And then in the optical also you see the changes. I wanted to put it with color and with the size of the ball, basically how it changes, right? And here we see this degeneracy and also how the methods that were before we had this meeting were not necessarily agreeing, even in the stars that are bright and very well known and very well studied, okay? So this is why we care about parameters. This is why we care about metallicity. This is why we want to get log Gs for these stars, because we want to know their parameters well. And if we know those ones well, then maybe we can trust evolutionary models and get masses and radius that will have a smaller uncertainties, and then we will be able to characterize them properly. So conclusions. The estimation of metallicities for M dwarfs is a degenerate problem. It was something that was avoided for a very long time, but there is very brave people sitting here that are willing to work on this, and we're getting results, and this is really exciting. Synthetic models for the cool stars are more complex than for hotter objects, just because we have also, one thing that I can mention is just molecular absorption, right? However, we have better and more complete models now, also for the atmospheres. We have better data and better facilities that allow us to get standard methods for M dwarf stars. When I say standard, it's basically the ones that we have been using for FGK stars, using high resolution spectra, either in the visible or the near infrared. So we can start getting effective temperatures, log G and metallicity and Bisonize and other things that you get from that. Some of them assuming certain things, some of them not. And there are still challenges. Something that I think we all agree is that the normalization is an issue for M dwarfs just because of their opacities. The interest for metallicities has shifted from galactic studies to exoplanetary studies. And this is something that is true till date. M dwarfs have the most interesting planets. It's not because M dwarfs are the coolest stars. It's because also our methods are biased. It's way much more easy to find a rocky planet around an M dwarf than around a G dwarf. Okay, so there are some biases there, but the ones that we've been able to find now with the methods that we have are around these stars, and that's what it's called usually the M dwarf opportunity. We can get reliable metallicities. We can discuss that with the people that maybe can tell me that, no, we also get precise ones. But I think we're limited in our precision, which affects the derivation of the parameters for M dwarfs. And I don't know if we will be able to solve that or not. And with that, I thank you for your attention, and I'll be happy to answer any questions. Thank you.
Thank you very much, Bárbara. Such a nice talk, and I've loved it. I come from galaxies and understood everything, so it's great, at least for me. So now questions, please.
Hi. Oh, thank you very much for this nice talk. Really, I enjoy very much with it. My question is about what happened with the extinction. We are considering that not interstellar extinction is happening here.
The things that you have to remember is that these are very faint stars. So basically, we're looking at very close by stars. So extinction, unless we know that it's something very, when I say close, I'm talking about parsecs. And I'm not talking about 100 parsecs. I'm talking about 48 light years, 80 light years, you know, like something that's close by. So unless I know in an extinction map that I will be looking at a place that maybe there is dust or something, usually we don't consider that. Like the stars, for example, that I was showing before, these ones are really close by stars.
But now it's possible to check right now with Gaia data. In fact, no? It's so.
We can do. But for example, for this object, extinction, I don't think it would be something to worry much about. I did some work, for example, with VVV. Okay, the Vista Variables of the Via Láctea is a survey that it's being done with a 4-meter telescope that it's in Chile. And we're looking at the bulge and part of the disk, and we extended this to look at larger distances from the bulge and also basically get all the disk that we could get. And one of the things that we wanted to know was, it's a near-infrared survey, it's very deep. And we wanted to get, for example, the M dwarfs. And in that case, indeed, we have to deal with extinction. But even in that case, I was very lazy, and I chose the tile that basically had almost zero extinction, close kind of to the bulge. And then I derived photometric distances, and the farthest M dwarf that I could see was an M0, so it was the most massive one, and it was 1 kiloparsec, and I'm not even sure that actually that's an M dwarf.
I don't want to be, the only asking that. But did you already text something connected with the spectral energy distribution, not only with the low resolution spectrum, but also with the photometry, the collection of photometry we have in the literature for every star here? So did you?
The first part. So you said the energy, the spectral energy distribution, yes?
Exactly. You already obtained more or less these two values, effective temperature and radius, or effective temperature, longitude, and metallicity, using this equivalent to optical low resolution, but it.
For example, the fitting of the SED comes here for the luminosity. Okay, so for the interferometric method, what we get is the angular size of the star, and we can derive the physical radius if we have the parallax, and we have the flux or the luminosity. And basically what it was done, it was to get an SED, fit the photometry where we could, and basically get the flux, and then get temperatures. So these two things are linked because they came from the same thing. And this luminosity is the luminosity cited here. So for these values, what I did was to trust this luminosity that comes from the SED fitting and see what do I get.
Yes?
Thank you very much. Very informative. I've come a long way from thinking that metallicities are very boring to thinking that they're very, to really liking them.
Right?
So you promised us what is the metallicity of M dwarfs. Mostly you talked about how to determine the metallicity of M dwarfs. So now let's come back to what is the metallicity of M dwarfs. You mentioned shortly it's basically solar what you see. How far out can you go, M dwarfs? Yeah, how far out can you go now to do metallicity studies? What's the distance of these? Are you really only within 100 parsecs?
Advantage, for example, of studying M stars with low masses, so we're not talking about giants, we're talking about main sequence M stars, it's that they really dominate in number, right? And also, we can take advantage that the halo crosses our disk. And we have stars that are crossing right now our disk, and because of their kinematics, we know they're halo members. One of the things we've been having problems with is that when we select, for example, common proper motion pairs in order to have metallicities from the FGK primary and assign those ones to the M dwarf secondary, it's basically that limitation. We don't go to the expected metallicities of subdwarfs, extreme subdwarfs, or ultra subdwarfs. So that's one of the things that we have issues with trying to get those metallicities. Something that we discussed in this workshop was basically going now that we have techniques that don't depend on external things, but they depend basically on the atmospheres, the model atmospheres, and do synthesis, for example. It's to go and get now subdwarf spectra with a high resolution spectrograph and try to get, if we get metallicities that we should expect of. What we know that we are going to find is that probably it's going to be challenging because the features are going to be weak.
Stick with the what are the metallicities. So what's the distributions that you get? Have you any extremely metal poor stars? I mean, you don't need to go to subdwarfs. Just take the brightest M dwarf.
So what I'm telling you is the problem is that we haven't calibrated with these methods all the way down. So we have to rely on what people are studying the galaxy using other stars. For example, the ultra subdwarfs, I don't think anybody has measured really a metallicity out of it, but we assume that it's -4.
How many ultra subdwarfs, how many metallicities, reliable metallicity measurements do you have for M dwarfs? Yeah.
Literature? Of them, but most of them are going to be disk dwarfs. And
will
you want the range of metallicities that basically we can get, it's limited to what we can see. So we have from -0.8 dex till 0.5. And sometimes you have 0.6, but I think those ones are not real values, and it's a problem of the fitting of the models.
How far out will you be able to go with the ELT, for example? How many kiloparsecs with the ELT?
Calculation, and that's something that I should do. Right now for the ELT, it's thought, there is a spectrograph that it's a espresso thought that will be a high resolution one, but that one is visible. So there's gonna be a disadvantage for the M dwarfs because M dwarfs are faint, and it will be great to have a near infrared spectrograph there.
Of the problem.
That's something. Now, I understand SDSS, for example, has done a lot of work. I think in what you're referring, it's like distance, right? You want to know how much I can see into the halo. That's your question?
Yeah, I'm going more towards the center, but...
Okay. So, for example, with VVV, that's a photometric survey. And the farthest M dwarf that I could detect was 1 kiloparsec.
You could go far, you could gain maybe 4 or 5 kiloparsecs within the disk.
For spectra, I'm not sure. We can do the calculation.
Thank you very much. Great.
Sure.
Any other question?
Okay, thank you very much, Barbara. It's a very nice talk. I also enjoyed it a lot. One point I have, I'm not sure about. You mentioned one of the spectra in the near infrared where you're showing calculation and fitting, and you said they are water vapor lying on the atmosphere. Do you mean the stellar atmosphere?
Let me see. This one.
Yeah.
Yes.
So all those lines are water.
I mean, the
Art.
yeah. So these are spectra that are high signal to noise. It's low resolution. It's K-band. This is a resolution of 2700. I'm showing 3 different types of stars. So basically, it will be 3 different spectral types. So an early, a mid, and a late. And what we see is that as you go to cooler temperatures, water absorption becomes really important.
Water absorption in the star.
In the star, yeah, because I have cleaned this from tellurics. I clean our atmosphere. So because of that, I always thought that this was residuals from the tellurics, and it wasn't.
Well, right. Okay.
Come, if you don't trust it, come and see, and you will see that everything is here.
Maybe we can talk about that later on, but my main point is that there is so strong absorption of water in the star that's going to be a problem for detecting atmosphere in the planets around those stars, because you will not really know whether the absorption came from the stellar or the planet's atmosphere. So that's why I was interested in that.
Well, it depends on what you do. I think if you do, if you were going to do this in the near infrared, maybe it would be a problem, but if you do it in the optical, it will be not, because this water absorption happens in this region. Okay?
I mean, in a given wavelength, it's the same in the star or in the planet. So, I mean, you have a fainter band of water in the visible, but they're both.
You're saying, so I don't understand your question. So, are you talking about transmission spectrography?
Yes.
Challenge. I mean, the whole thing. It's
No, because so far, when in the planet we are looking at, we assume that the flat spectrum of the star in the near infrared about water. So when we see these features, we know, okay, they are from the planet. So for them, there will be a problem.
I don't know. Actually, David is moving his head. So if you have the answer, you can answer that. I'm not an expert on transmission spectrograph, transmission thing. I'm very skeptica. Yeah. Of the.
You had the absorption in the star.
And actually, I'm gonna go to YouTube saying this. Because first, the resolution that we're getting those things is really bad. You can fit whatever you want. So in all those papers, I know it's a lot of people working really hard on that. So it's not that I'm not taking into account that. But usually it's very, I could fit that with this or with something else. But I think David has the answer that you wanted, that it's because of water. So David is right after you.
There is water absorbing in the star's atmosphere. Yes.
Yeah, this is water.
Okay, so that's my...
This is, you know, like basically the spectrum gets like that. But I think he can answer you, he can answer your question better.
You can distinguish by the planet that is moving during the transit, and you distinguish the absorption from the planet from the absorption of the star. As in the other detection that we've done in H-alpha or in calcium or in sodium, you see the radial velocity for the planets moving and distinguish one from the other.
So then you take the spectrum out of those two, and then you subtract it, and then you're supposed to get the spectrum from the star.
I've got one, a very simple one, and probably a result of my ignorance. Did I get right that did I get right that when you get higher metallicities, you got the giant planets, and when you get low metallicity, you have the the Earth-like planets?
Yeah. So the planet-metallicity correlation, which has been quite established for FGK stars, indeed shows that. So stars that exhibit giant planets seems to be more metal-rich than stars, for example, that have no planets. The thing is that when I say metal-rich, I'm including the sun. Huh? It's not that I'm saying that and you can see that there is a distribution.
What I mean is in the solar system, we have both. So if it is...
Yeah, so it's the presence of a giant planet. I'm not ruling out the presence of smaller planets. Actually, in the co-accretion scenario, what we think is that several things start building, and there can be a lot of other things. No, it's just that if the system has a giant, this could happen. What we see, though, for stars that have Neptune or Earth-sized planets, the distribution is flat. So that's why it's always based on the giant planets. But that's a really good question. I'm not ruling out that there is a giant and there are other sorts of planets. It's the presence of the giant.
Is there any other question? So if not, thank you again.